concepts of temperature and heat are often thought to be the same, measures of hotness and coldness. Lava bubbling from a volcano brings to mind high heat and high temperature. On the other hand, seeing huge icy glaciers makes us think of low heat and low temperature. Yet, although temperature and heat are related, they are actually different concepts. In this section, we will see how temperature is measured, look at the differences between temperature and heat, and finally discover that heat is just a form of energy. Temperature is familiar to all of us, and knowing temperature is very important in our daily lives. We decide what clothes to wear before going outside based on the air temperature reported by the Weather Bureau. We know how long to bake a cake for a given oven temperature. Our cars run only because the coolant system monitors the engine temperature and keeps it within a safe range. To measure the temperature on a macroscopic scale, we use a device called a thermometer. A thermometer can be based on a variety of principles: the expansion of a liquid such as mercury in a sealed glass capillary tube, the differential expansion of a bimetallic coil, or the change in color of a liquid crystal. For a thermometer to be of any use, it must be calibrated to a particular temperature scale. The most practical temperature scale is linear. Thinking back to your basic math, what is the minimum number of calibration points you need to produce a linear temperature scale? Correct. You need at least 2 calibration points. The calibration points are usually based on the relative measurement of some physical phenomena, such as the freezing and boiling points of water. Today there are 3 temperature scales in use in the United States: the Celsius scale, widely used in science and industry; the Kelvin scale, primarily used in scientific applications; and the Fahrenheit scale, used in people's daily lives. In 1745, Carolus Linnaeus developed a centigrade scale based on the freezing point of water at 0 degrees centigrade and the boiling point of water at 100 degrees centigrade. The Kelvin scale was set forth by an international committee in 1933. This scale uses absolute zero, the lowest point on the scale, as one standard point, and the triple point of water at 273.16 kelvins as the other. Note that one does not use the term degrees with the Kelvin unit. Do you remember what the triple point of water represents? Correct. It's the temperature at which liquid water, ice, and water vapor coexist in equilibrium. Following the development of the Kelvin scale, the centigrade scale was renamed as the Celsius scale and modified such that the triple point of water is 0.01 degrees Celsius, and 1 degree Celsius has the same magnitude as 1 Kelvin. The Fahrenheit scale, developed by Gabriel Fahrenheit in 1724, was developed using the temperature of freezing salt water as 0 degrees Fahrenheit, the temperature of freezing water as 30 degrees Fahrenheit, and the human body temperature as 96 degrees Fahrenheit. Later he adjusted the scale, setting the freezing point of water at 32 degrees Fahrenheit and fixing 180 degrees between it and the boiling point of water at 212 degrees Fahrenheit. In the United States, we still use the Fahrenheit scale for cooking and describing the weather. Most other countries use the Celsius scale for such purposes. Because the Fahrenheit and Celsius scales are both linear, we can graphically derive a linear equation to convert values from one scale to the other. Let the x-axis represent degrees Celsius and the y-axis represent degrees Fahrenheit. Remember, we need 2 points to determine our line. Which 2 points should we choose? Correct. We should pick 0 degrees Celsius and 32 degrees Fahrenheit, the freezing point of water for each scale, and 100 degrees Celsius and 212 degrees Fahrenheit, the boiling point of water for each scale. Now we can draw the line representing our conversion equation. What are the slope and y-intercept of the line? Correct. The slope is 1.8 and the y-intercept is 32. Therefore, an equation for converting from degrees Celsius to degrees Fahrenheit is degrees Fahrenheit equals 1.8 times degrees Celsius plus 32 degrees. How many degrees Fahrenheit is 25 degrees Celsius? It's 77 degrees Fahrenheit. Now, how many degrees Celsius is 59 degrees Fahrenheit? It's 15 degrees Celsius. Our perception of temperature is rather subjective. A January temperature of 10 degrees Celsius, 50 degrees Fahrenheit, would seem balmy to a person in Chicago, but cold to a person in Los Angeles. Looking at temperature in this way, as a perception of warmth and coldness, doesn't help us properly define what temperature really means in a scientific sense. Looking at an object on a microscopic scale, we see that the molecules comprising it are in constant motion. As we heat the object, the motion becomes more vigorous. On a macroscopic scale, if you touch an object with a high temperature, you perceive the subsequent transfer of energy as a sensation of extreme warmth. This is a result of the energetic molecules in that object colliding with those in your finger. So what do you think is the relationship between the temperature of an object and the molecules that comprise that object? Correct. The temperature of an object is related to the kinetic energy of the molecules in the object. Whenever two objects with different temperatures come into contact, energy flows from the hotter object to the cooler. We call this flowing energy heat. What happens to the temperatures of the two objects? Correct. The temperature of object 1 increases, and the temperature of object 2 decreases. What do you think happens when two objects at the same temperature are in contact with one another? Correct. No heat flow takes place between them. We say the two objects are in thermal equilibrium. Going back to the two objects at different temperatures that come into contact, what can you say about the final temperature of each object? Correct. Eventually, the two will reach the same final temperature. They will then be in thermal equilibrium. If one object is in thermal equilibrium with two other objects, what can you say about those other two objects? Correct. The other two objects are also in thermal equilibrium with each other, and therefore also have the same temperature. This is known as the zeroth law of thermodynamics. Suppose we have a hammer and a nail that are initially at the same temperature. Then we pound the nail into a board with several blows of the hammer. What do you think happens to the temperature of the nail? Correct. The nail increases in temperature. Where did the heat energy in the nail come from? Correct. It came from the kinetic energy of the pounding hammer. The idea that heat is a form of energy may seem obvious to us today, but not so long ago, the idea was unpopular. Up until the mid-19th century, the popular belief was that heat was a fluid substance known as caloric that flowed from one object to another. In the late 18th century, Count Rumford noted that a cannon boring machine produced heat as long as it was working. He concluded that heat was the result of mechanical processes involving the motion of molecules. Finally, in 1847, James Joule showed quantitatively that mechanical energy can be converted into heat, and as a result, the caloric theory was soon abandoned. Let's do an experiment with our own version of Joule's apparatus. As you can see, two falling objects drive a set of paddles in an insulated container filled with water. What provides the mechanical energy in our experiment? The two falling objects provide the mechanical energy. How is the mechanical energy transformed into heat energy? Correct. By the action of the paddle wheels moving in the water. What is the mechanical energy expended by our apparatus as shown? Correct. It's 19.6 joules. Joule knew that by definition it takes 1 calorie of heat to raise 1 gram of water 1 degree Celsius. How many calories of heat are required to raise the temperature of the water by 1/100th of a degree Celsius in our simulated apparatus? Correct. The answer is 4.68 calories. So what is the mechanical energy equivalent of 1 calorie of heat? Correct. Our calculated mechanical equivalent of heat is 1 calorie equals 4.19 joules. Now let's go back to our hammer and nail experiment. The mass of the nail is 5.0 grams. The temperature change of the nail is 10 degrees Celsius, and it takes an input of 0.11 calories of heat per gram to raise the temperature of the nail 1 degree Celsius. What is the equivalent work done by the hammer? It is 23 joules.